Hello, I'm the Dark Master, and welcome back to the Tale of the Trilobites. Last time I answered the question of what is a trilobite and where they fit into the broader family tree of life, so check that out if you'd like to learn more on that topic. But in today's video, we shall be explaining the anatomy and many technical terms you will see when discussing trilobites, so that you can better understand them as well as get a better understanding of their anatomy. As being invertebrates, their body plan is not as familiar to us as compared to, say, elephants. So, without further ado, let us start with a general overview of their exoskeleton makeup before going into the specifics. Alright, so trilobites, like most arthropods, have heavily mineralized exoskeletons, which consist of three distinct layers. A very thin outermost layer that is rarely preserved, called the epicuticle. Then there is a middle layer that is slightly thicker and more often preserved, called the exocuticle. And then there is a third, even thicker layer, called the endocuticle, which is what is normally preserved and what you normally see when looking at their fossils. This exoskeleton can usually be smooth in a lot of species of trilobites, but a lot of other species of trilobites have a variety of textures referred to by trilobite specialists as prosopon, though if you want, you can call them exoskeletal sculptural elements or just texture. These can be all sorts of things, from pits that in life could have held sensitive hairs akin to those seen on some living caterpillars, nodes which, while still are understudied, may have had some sensory or visual functions related to sexual selection. Ridges which, depending on the species, could have helped them burrow through fine silt or sand. Then there are tubercles, which are round growths that are also sometimes called granules if they're very small. They are believed to have had two main roles, one as a form of camouflage in certain habitats, and also as a form of strengthening the shells against predation, especially against cephalopods, which apparently had issues grasping onto tubercled rough surfaces compared to smooth ones due to their tentacles. Last but certainly not least are spines. Now, to clarify, only the really small spines are considered part of the prosopon. The larger ones that we shall discuss in a bit are not considered prosopon. Some trilobites have spines on spines. And keep in mind, a lot of these categories have a lot of overlap with many transitional variants. Truly, the diversity in trilobite exoskeleton coverings could frankly be their own video, but I think for now it's best to go on to the trilobite body plan. You know, what this exoskeleton makes up. Alright, so the trilobite exoskeleton, much like that of insects, is divided into three sections. It is in the name, tri, which means three, and lobe. But unlike insects, it's not just horizontal, though, as well as vertical. Indeed, it is specifically these vertical divisions that give the group its name. There is the central axial lobe that would have covered the gut, mouth, and other organs, and the right and left pleural lobes that would have covered the gills slash legs, as well as had the eyes and antennae and such. All trilobites had these features, as it's a pretty diagnostic trait and fundamental part of their biology. Perhaps easier to understand, however, are the horizontal sections, often called tagamata, though segments work fine too. First is the cephalon, which is the head region and has the eyes, antennae, and such. The thorax, which has a very varying number of segments, which in some species allow enrollment, and covered the leg slash gills. Then finally we got the pygidium, which is basically the tail of the trilobites. Unlike the lobes, each of these regions does have quite a bit of variation and stuff to talk about. So let us start with the top and give trilobite heads, some due. Perhaps the most famous part of the trilobite's head, and frankly their anatomy as a whole, whenever anyone talks on the subject, are their eyes. While yes, they were not the first animal with eyes, as some people claim, they were the first to have sophisticated eyes, those being compound ones. You see, unlike us humans and other vertebrates, whose single lens can change shape as well as those of cephalopods that convergently resemble ours, those of arthropods have immobile lenses that are compensated for by having a large number of said lenses. Unlike those of modern invertebrates, the eyes were of even higher quality, being literally made of actual crystal, shaped like the lenses that wouldn't be invented by optical scientists until over 300 million years later. So much for wise men, eh? These guys figured it out with the brains of bugs. These eyes were so great, they had very little distortion. One genus, Erebonochile, developed literal eye shades to help dampen light pollution, even. With regards to the eyes themselves, there were three categories: the holochoroidal eyes, the schizochoroidal eyes, and the abathochoroidal eyes. The holochoroidal eyes represent the basal condition found in nearly all orders. Unlike the other two, the eye lenses are very small and in direct contact with each other and can range in number from 1 to more than 15,000 per eye. The second type of trilobite eyes, the schizochoroidal eyes, are only seen in the order Phacopoda. In this case, the eye lenses are much larger and fewer in number, at most numbering 700. Each lens bears an individually separated lens from each other by sclera between the lenses, and it's very deep. It is believed that this eye developed via the process of paedomorphosis, which is the process of retaining juvenile traits into adulthood. A famous example of paedomorphosis that you'd be familiar with is the modern axolotl, with its larval gills maintained even into adulthood. Proof of this can be seen in the preserved immature trilobites of the Cambrian, which predate the Phacopoda and basically have miniature versions of the schizochoroidal eyes in terms of form. Why exactly they evolved this eye is unknown, but it might have had an advantage in certain environments. Third and least common are the abathochoroidal eyes, which are seen only in one suborder of Agnostida trilobites, the Eodicina. These eyes have an even smaller number of lenses, only 70. They are small and separated by sclera that are shallow compared to that of the other groups. It seems that these eyes degenerated over time as an adaptation to deepwater pelagic life. Outside of these three major categories, trilobite eyes as a whole have a lot of variation. There are ones with eyes on stalks for remaining buried under sediment, like the genus Neoasaphus. Some pelagic species had massive, huge eyes, like Opicturella and Telephinus, which help them detect predators. Other trilobites went in the opposite direction, especially fossorial and deep water species, and reduced their eyes, like in the genus Trimeris, or lost them entirely, like the orders Agnostida and Trinoculata. In fact, we have so many trilobite fossils, we literally even see the process of species evolving and losing their eyes over time. Moving on from the eyes to the rest of the head, while not as famous or as well documented, it is similarly complex and diverse. First, there is the glabiella, which is believed to have been where the mouth/anterior digestive system was located. Behind that is the occipital ring. Then there are the other regions of the head, called the cranidium, which itself was made out of two primary regions: the fixigene, or fixed cheeks, and the liberigina, the free cheeks, which is separated by suture lines, which would have been very important for trilobites whenever they decided to shed their exoskeleton. The location of these facial sutures are very useful for taxonomy, consist of three main types. Proparian sees the suture angle forwards of the genal spine. Gonotoparion sees the suture going down into the genial spine, and the Opisthomoparyon sees the suture ending behind the genial spine. Speaking of spines, they have different names based on their locations. They don't really matter, these names. You can see them in this diagram. And their size and shape varies endlessly to the point where I couldn't even begin to give a complex overview of the entire variation of spines in trilobites. There are many other suture pattern subvariants that I shall cover when I cover individual orders in the future of this video series. But now, let us look at the trilobite's body or thorax, the next main part of their anatomy. The thorax is divided, much like that of millipedes and other living arthropods, into several thoracic segments. Each segment would have an accompanying pair of legs and gills, but I'll go more in depth on that in a later part of this video. Returning to the thorax itself, it has perhaps the greatest level of variation of any trilobite body part. At one extreme, there is a strange species of trilobite, Scalamanensia fusilis, that completely lost the thorax, fusing its head, body, and pygidium into one large protective dome. Agnostids are another group that are famous for their small thoraxes, numbering only 2 or 3 segments. On the other side of the spectrum is the basal species of trilobite Balcoraxenia dalei, with over 100 segments. But most trilobites are closer to the middle, with like 10 to 15 segments. These segments, in addition to serving as protection, allowed trilobites some form of flexibility. While early forms could have done some lateral articulation, later forms were probably only limited mostly to vertical articulation, better known as enrollment. Enrollment of trilobites is where they basically act like a roly-poly and roll up when confronted by predators. While many basal trilobites lacked this trait, post the Cambrian, it seems predation pressures made it pretty much universal. There are 4 main types, distinguished by the mechanisms of their enrollment. First, you have incomplete enrollment, also called a cylindrical enrollment by some sources, which, true to its name, has the thoracic segments not completely enclose the ventral or bottom surface. While this is commonly seen in more basal trilobite groups like oleanoids as a form of transition from non-rolling forms to more advanced enrollment styles seen in later trilobites, there are also some later genera like Selenopeltis that convergently evolved a simplified form of enrollment for unknown reasons. Double enrollment, also called a spiral enrollment by some sources, is distinct in that the tail/pygidium and hindmost thoracic segments are left hidden underneath the front edge of the head/cephalon. This is even rarer forms of enrollment, being only known from early Cambrian trilobites like Elyphosocephalus. No idea why, it seems perfectly fine though. Discordial enrollment, also called by some the basket and lid enrollment, involves the flexing of only the anterior or front part of the thorax. This enrollment is very common, especially with trilobite groups bearing large heads like harpids and trinoculaids. The fourth and final type of enrollment is phaeoridial enrollment, which is distinguished by how all the thoracic segments participate equally in the enrollment. And basically, if you've ever seen a roly-poly roll-up, that's basically what this is. It's the most commonly seen of all the enrollments, being found in many groups like Phancopids, asaphids, and agnostids. Enrollment of all kinds was supplemented in various lineages by spiny protrusions of all sorts of diverse shapes and orientations and arrangements on the head, thoracic segments, and the last body segment that we shall be discussing, the Phaegidium, was particularly helpful in helping to prevent predation. The pygidium of the trilobite is basically the tail of the animal. It consists of a collection of few segments that had many functions. The primary one was likely defensive, given how often they have spines and nodes. There are four main categories distinguished by size, but this is more of a spectrum than a hard and fast category system. First and most basal are those with a pygidium that is much smaller than the head, called the microphagius. Those with one only slightly smaller than the head is called a sub-isopygius. One with a tail that is the same size as the head are isiopygius, and lastly, those with a pygidium larger than the head are called macropygius. Cool, but everything so far has been solely dedicated on the dorsal or top half of the trilobite, which you might have noticed. And honestly, that's because it is what is most often preserved. But there is a whole other side to the anatomy of trilobites, which we shall discuss now, that involve more soft tissue that isn't often preserved. Alright, so compared to the hard upper skeleton, the rest of the trilobite's anatomy is nowhere near as well preserved, with only 19 species having anything preserved at all. This was likely due to how much smaller these parts of the body were, and due to not being as well mineralized. But we can get, albeit somewhat of a vague feeling of how these animals were like. First, they had antennae that likely had a similar function to those in insects and crustaceans to detect food or mates. Their legs were very simple, and unlike other arthropod groups, they never really developed modified legs in their history, retaining the basal condition you see in earlier invertebrates. However, something interesting is how the legs had growths that are believed to have been gills, meaning while they walked, they breathed. One species, the basal Orliniids serratus, had a unique additional pair of cerci, which are antenna-like sense organs that were located near the tail. Though how common these were on the group as a whole cannot be determined at this time, and it's possible that this is something exclusive to this group. We just don't know. Perhaps the most unique aspect of these ventral structures is the hypostome, which is basically the mouth part of the trilobite and was used in processing food. They have been very useful at clarifying trilobite classifications and ecology, and while I'm not going to get into the classifications in this video, there are main types distinguished by how they are positioned on the trilobite's head. The Naton type has the hypostome being in line with the front of the gabiella. The countermeanate, which sees the hypostome attached to the anterior doubler, which is part of the underside of the head that's not really relevant otherwise. And a third category, which has the rarest variant, where the hypostome is attached to the doubler but not aligned with a Galabriella. Very rare, only seen in Cherurid trilobites. It's believed those with the natant hyposomes were just generalized particle feeders with no need to modify it, and as such believed to be mostly the basal condition, while the counterminerant Hyposomes are believed to have been more predatory, which led to far more varied forms due to different prey preferences. But now, let us go on into the even more poorly understood interior anatomy, which is rarely preserved except in a few Agnostid specimens. And as such, we have to base it mostly on living arthropods. We know that trilobites likely had a gut, some form of reproductive system, as we have found eggs as well as embryos, nerve cords, and some form of excretory system. But until future discoveries are made, there's not really a lot solid that we can say at this time. In conclusion, I hope now you understand some of the terminology that trilobite specialists use, as well as their overall structure of the group. There's a lot more stuff I could talk about, but it mostly applies to only certain groups, so I will be going over those terms when they are relevant. I hope you liked this video. If you liked it, consider subscribing. But if you loved it, consider liking it as well. And join me next time on the Tale of the Trilobites, where we shall start our coverage of the orders of the trilobites with the Redlichiida, the earliest trilobites.
Sorry, man, for feeling the way I do. Oh yeah, open wide and they'll shove in the meaning of life. Oh yeah, not for me, I'll do it on my own. Oh yeah, open wide and I'll swallow the meaning of life. I can't make you work your way.